Okay, so one of the things we can do with our stoichiometry and our skills that we're developing using mold-to-mold bridges in the context of reactions is we can start to make predictions associated with limiting reactant problems, okay? So limiting reactant problems are a really common type of problem where you're given information about two reactants, two or more reactants, right? And you're asked to make a prediction, all right? So the first step that we always do when we're looking as to whether we have to sort of go through the limiting reactant process or not is, do we see that? If you're reading a problem and it looks like you're given information about more than one reactant, right? Tell yourself right away, right? If that problem is asking me to make any prediction at all, how much product is made, how much reactant is left over, what the yield is, any reaction at all, any prediction at all, right? Then you know it's a limiting reactant process and you're going to follow the same steps that we outline in this video, right? The idea behind a limiting reactant is pretty straightforward. There's one of the reactants that's involved in a reaction that runs out. And because it runs out, it limits the production of product. It stops the process. It's like, an ingredient in a recipe that you run out of and then you have to stop cooking. That's essentially what it is. Now, you might have other ingredients and we'll have other reactants that are left over. And those we say are in excess. For limiting reactants, you'll see me abbreviate it LR. You'll see me abbreviate excess reactants with XS, all right? So excess just kind of means what it says. It's stuff that's left over. We didn't run out of it, but we still can't use them because one of the reactants went away and is gone, right? So it's a general process here, but again, it's one of these situations where, the more examples we do, the more comfortable we get with it. The way that I outline limiting reactant problems, and if you know a different way to do it and you're comfortable with it, go ahead and do it. But like I said, I just like to present one consistent way that makes sense to most of the students that I run into. What we're going to do is we're going to take that reactant information that's given to us and we're going to turn it into product information. We're going to essentially get the same unit and identity so we can make some comparisons, okay? Then, all right, that product info we refer to as the yield, all right? The yield that matters is the smallest. Remember, the whole idea with the limiting reactant is that it runs out and it limits production. It's an ingredient that goes away. So when we see, all right, when we do these conversions and we see what our results are, the smallest matters, right? The smallest matters. And then what we'll remember is that if we're asked to do anything else in the process, the limiting reactant controls everything. It's the thing that just dictates how much is made of a product, how much of the other reactants are used. It has complete control of the actual reaction and what occurs. So we're going to start with a very, very, very simple example, but it kind of illustrates the point in a really clear way. And if you get this simple example, then you'll get the more complicated chemical examples that we do, all right? So we're actually going to kind of start off with sandwiches, all right? So what we're going to do is we're going to make up a chemical reaction for a sandwich where we have 2 bread plus 1 cheese plus 3 meat gives a sandwich, okay? And what I'm going to do is I'm going to give you reactant information. I'm going to tell you that you have to start with 5 pieces of bread, and you have to start with 2 pieces of cheese, and you have to start with 3 pieces of meat. And what we're going to ask about is we're going to ask to make a prediction, okay? How many sandwiches can we make? Now, you already know the answer, but that's why I kind of give you this simple example. So hopefully you can see this and say, okay, well, I can really only make 1 sandwich based off of this reaction here, because if I'm using 3 pieces of meat, as soon as I use these, they're gone. And then my sandwich production stops. And it doesn't matter how much cheese I have and how much bread I have, as soon as I run out of meat, everything stops. That simple idea is the exact same idea associated with limiting reactant problems, all right? But let's follow our process and see mathematically how this will make sense. What I have here is a balanced reaction. So what I'm going to do is I'm going to take this reaction, and in chemical context we use mole-to-mole bridges. I'm just going to kind of show you like in a ratio way, all right? I can't compare directly bread to cheese to meat. They're different things. But what I could compare in terms of bread, cheese, and meat is how many sandwiches each could possibly make. I could build a set of common units. And that's what this conversion step is. So we're going to look at our product sandwiches. And we're going to say, okay, 2 breads give me 1 sandwich. And I'm going to write sandwiches, sand, because I'm just getting lazy. And so those 5 pieces of bread, what this conversion factor tells us is the max amount of sandwiches you could possibly make is 2.5 sandwiches. All right. 2 pieces of cheese. All right. I can use the mole-to-mole bridges here. Well, there's 1 piece of cheese for every 1 sandwich. So this means that these 2 pieces of cheese, they could possibly make 2 sandwiches. And finally, 3 pieces of meat. Based off the reaction given, 3 pieces of meat give me 1 sandwich. Oh, so then when I do this conversion, all right, I see that I do get 1 sandwich out. Now look at, I made this point earlier. You cannot compare bread to meat to cheese, but you can compare sandwiches to sandwiches to sandwiches. These guys now have the same unit and identity, right? And that's what we're going for. Now these numbers I can compare, and whichever one is the smallest tells us how much of the product is made. So 5 pieces of bread could possibly make 2.5 sandwiches. 2 pieces of cheese could possibly make 2 total sandwiches, but 3 pieces of meat can only make 1 sandwich. So then how much is made that 1 sandwich? Okay. This we would refer to as the theoretical yield. The theoretical yield. All right. And I'll talk about the, why we need to give it that name in a bit. Right. So here we've made a prediction, right, based off information that's given. But now we could do some other predictions. Well, how many pieces of bread are left? And how many pieces of cheese are left at the end of the process? Okay. So sometimes we're asked to calculate excess information. And that's where we use step 3 of the process. And we realize that the limiting reactant controls everything. The limiting reactant controls how much of the excess reactants are used. And this is a very important idea. I can convert from limiting reactant information to excess information. And when I do that, that's how much was used. So in the context of our sandwich example, this is going to make sense. Like if I ask you how much cheese is left after I make 1 sandwich. Well, I started with 2 pieces of cheese. I used 1, so there's 1 left. We can get to that mathematically in a simple way. And we're going to follow the same mathematical idea when we get to more complicated chemical problems. All right. The limiting reactant was meat. So I start with my limiting reactant information. And I use the stoichiometric coefficients to now convert over to other reactant information. And when I do that, right, this is how much of that reactant was used. When I want to find out how much is left, what I have to do is I have to take how much I had to start with and subtract how much was used. All right? So 3 pieces of meat will use 1 piece of cheese. I started with 2 pieces of cheese. I used 1 piece of cheese. And so I have 1 piece of cheese left in excess. That's how much is left in excess. So I want to just point that out what this is because we are going to do it for a chemical problem here in a second. All right. 3 pieces of meat tells me I used 1 piece of cheese. Take your limiting reactant information, convert it to the information about another reactant, and that's how much is used. If you do start minus used, That's how much is left in excess. And it's a common problem that you'll be asked. Okay. Now we could do the same thing with the 5 pieces of bread. Okay. And we know we started with 5. We know we used 2. Just make sure you could go through the process yourself in this similar way. But what I want to do now is tell you that if you understand how this works with sandwiches, now what we can do is we can go on to a chemically relevant example. Sorry for bumping that again. Now, everything we do with sandwiches, though, we're going to do in this more complicated scenario. This example is in your chapter 3 slideshow again, right? And it's actually slide number 4. And what you'll see is there's some interpretation to do. Because again, you're given a bunch of words. And you're asked to interpret names to formulas and get a balanced chemical reaction. The interesting thing about interpreting the words on slide 4, and please pause the video and take a second to read it, is that what you'll notice is it's different than the last example we did in the last video because you're given information about multiple reactants. It's not just a simple conversion problem, it's a limiting reactant problem because there are 2 reactant bits of information that you're given and you're asked to make a prediction. Okay, so take a second, try to interpret the words, right, into chemical formulas, and then from there try to balance it. So hopefully you can see that the balanced chemical reaction is 2N2H4 liquid, and you wouldn't need to know that that's hydrazine, right, plus N2O4 dinitrogen tetroxide liquid gives me 3 nitrogen gas and 4 H2O gas. So hopefully you're able to do that interpretation step and build a balanced chemical reaction. We still need a balanced reaction because we're still going to be asked to making predictions. We're still going to be doing conversions, so this is a necessary first step. Now, how I know it's a limiting reactant problem one more time. You're given that we have 1.00 times 10 squared grams of N2H4 that we're reacting. And we're also reacting 2.00 times 10 squared grams of N2O4. Information about 2 reactants. Can I compare directly N2H4 information and N2O4 information? And the answer is no. These do not have the same number and unit, so I can't compare them directly. I do not know what the limiting reactant is because these numbers do not compare. So I follow my limiting reactant process, and what I'm going to do is I'm going to take my grams of N2H4 and I'm going to turn it into grams of N2, right? Because we're asked to make a prediction about N2. And I'm going to take my grams of N2O4 and turn it into grams of N2. So I'm going to do 2 different conversions, right? Then my final answer will have information that has the same unit and the same identity, and I'll be able to compare. And which one do we pick? We always pick the smallest one, right? The smallest one. So you should be getting pretty good at these conversion steps by now. I still want to show you these, all right, for this example. Let's do the top conversion first. I look up in the periodic table, I get 32.052, this is the 3, grams of N2H4 for every 1 mole of N2H4. I had different identities here and here, so again, I do my normal conversion steps. I'm running out of room here, so I'm going to have to rewrite some stuff, but that's okay. 2 moles of N2H4 and 3 moles of N2. Continuing my conversion, for every 1 mole of N2, we have 28.02 grams of N2. My calculator spits out 131.13 grams of N2 with 3 significant figures. We don't know what the answer is yet because we have to do a similar conversion with our 2.00 times 10 squared grams of N2O4. And so we do that. We look up its molar mass off the periodic table, and we get 92.02 grams of N2O4 is 1 mole of N2O4, right? Using the balanced stoichiometric coefficients. Remember where these guys are coming from. There's a 2 in front of the N2H4. There's a 3 in front of the N2. It'll be the same thing down here, okay? We have to get to N2 information. So N2O4 has a 1 in front of it, so 1 mole of N2O4, sorry. N2O4 has a 1 in front of it right here. So I use the stoichiometric coefficient there. N2 has a 3 in front of it, 3 moles of N2. 1 mole of N2, 28.02 grams of N2, right? We didn't have to go to grams, but because we were asked to calculate it, I just went ahead and went all the way to grams. As long as the unit and identity is the same, you can make your comparison. So here I get 183 grams of N2 and some decimal points, but I even stopped writing that number, okay? Because now, like I said, the general rule that we have is we can compare these guys as long as the unit and identity is the same, and we've done that, all right? So let's interpret these numbers. This amount of hydrazine can produce this much N2 max. This amount of dinitrogen tetroxide can produce a greater amount of N2 max. So which one limits our production? Which one is the limiting reactant, right? Hydrazine must be the limiting reactant because it can produce a smaller amount of nitrogen. That means that N2O4 dinitrogen tetroxide must be our reactant in excess. So what is my theoretical yield? How much nitrogen is produced? The smaller amount. And to the correct number of significant figures, you would say that it's 131.13 grams of N2. Okay, this follows, and hopefully you can see, this follows exactly what we did with sandwiches. We took reactant information, made a product information, reactant information, made a product information. I recommend circling the smallest just to always remind yourself that at the end of the problems, the yield, like what you actually predict is being made, is always the smallest one. We circle the smallest, all right, and then that's our answer. We've also identified the limiting reactant, so now if we want to do extra steps, such as calculate the mass of excess left over, we know what controls that. All right. So let's do that. So we're going to keep going with this problem now. We're going to say, okay, let's calculate the mass of excess reactant. Well, what determines how much of that excess reactant is used? Our limiting reactant. Our limiting reactant controls everything, and pretty much every conversion that we do after our initial conversion always starts with the limiting reactant because it's the orchestrator of what happens in this reaction. Okay? So, all right, I take my limiting reactant information, I convert to moles, I convert over to information about the other reactant. Just like we did with sandwiches. Now I'm going to go all the way to grams because what I asked you verbally for was the mass of excess reactant. The mass of excess reactant. So I know I can use the molar mass that I already calculated above. And we have 92.02 grams of N2O4 for every 1 mole of N2O4. And I plug this in my calculator. What I get is 143.548 grams of N2O4. These, though, when I do this conversion, do you remember what we did in the sandwich example? We're going to do the same thing here. We're going to remind ourselves that this is the excess reactant that has been used. So if I want to know how much excess reactant is left over, I started with 200 grams of N2O4. That was my starting amount. That was given to me in the problem. I just determined that I have 143.548 grams of N2O4 that have been used. When I take those two values and I subtract them, I pay attention to subtraction rule significant figure. This is good to the ones place. This is good to the ones place. So my answer is good to the ones place. My final answer is 56.452. Oh, it's only good to the ones place. Okay, my final answer is 56 grams of N2O4. That's how much is left over at the end. Okay? Again, this follows with what we did with the sandwich example. Once we identified our limiting reactant, we converted over to information about the other reactant and reminded ourselves that that's how much was used. Start minus used gives me how much is left. Okay? Even though it seems complicated, it's the same process again and again. I'm going to put one more thing, one more part to this example, because it's the one last thing that you're going to be asked to do in this chapter, kind of regarding making predictions associated with limiting reactant problems, just in general. And that's percent yield. So everything that we do on paper is theoretical, right? And essentially when we actually run experiments have error associated with them. So if we're supposed to make a certain amount of a product, all right, that's the maximum amount we will make. Now, there'll probably be something go a little bit wrong with the experiment that will limit our yield. And so what percent yield does is it quantifies how good our process is, all right? And what percent yield says is you take your actual yield, and that's going to be given in the problem, how much you actually get out, right? And then you divide it by your theoretical yield. And your theoretical yield, that comes from your pencil and paperwork. That comes from your limiting reactant problem. If you take those two values and you multiply by 100, that's your percent yield. So let's tack on another part of this example. So we're going to stick with the same example from the slide, okay? And I'm going to add that, okay, what happens if 36.51 grams of nitrogen were actually produced? What we can do is we can calculate our percent yield now, okay? Because we've already been through the process of determining what the theoretical yield was, okay? So let's calculate a percent yield. Our actual yield is given to us, 36.51 grams of nitrogen, okay? Our theoretical yield was 131.13 grams of nitrogen. I'm going to use an unrounded value right now, right? That was if everything went perfectly, right? That's how much N2 we should have got out. We only got out this much, right? So this is a measure, oh yeah, and then multiply by 100, right? So this is a measure of like the efficiency of our process. And the percent yield here is only 27.8%. But notice, it's only like one extra step. Now, it does give us some information about the process. Like I just mentioned, this process, if we only get that much out and on paper we should have gotten that much out, that tells me that we might need to refine the process. We might need to go back and look for different ways to run this reaction, different experimental settings, so we can maximize our yield, okay? But in the context of what you guys have to do, you know how to get theoretical yields from your limiting reactant problems. You follow the steps that we outlined in this video. It's one extra division, multiplication by 100 that you do at the end of a problem to figure out the efficiency of the process, the percent yield. So there's a ton here to get through. Watch the video multiple times. Do the practice problems in Chem 101, do the homework problems in Chem 101 and in your book. Make sure you contact me as much as you can. Any limiting reactant problem you ever run into, you're going to follow these steps. So again, we're trying to provide you with general pathways through these problems. So make sure you understand the identification, the steps involved, and then what you do to analyze the results, and you'll be set to go forward in this chapter.